So hi everyone, this is the Hamiltonian TCS seminar, and today this week we have Malory Marin, who is visiting us from Lyon, who is doing his PhD with Rémi Vatrigan here, and Nicolas Trottignon, who is also visiting this week. And during his PhD, he had very nice results about, in particular about parameterized analysis, of mixing times of fluid dynamics. But today he won't talk about mixing times. He will be telling us about geometric intersection graphs. So the floor is yours.
Thank you. So yeah, I will talk about subexponential algorithms for geometric graphs, and in particular Hamiltonian path and Hamiltonian cycle. And it is a joint work with both Rémi Vatrigan, my advisor, and Jean-Florent Raymond, who is also in Lyon. So I will start with an introduction, because maybe some of you are not very familiar with geometric intersection graphs and in particular robust algorithms. So let's start with a small introduction. So in fact, it will be a very large introduction because I will introduce all the tools I need to prove my main results. So it will be quite long. So let's start with some definition. So take a family of objects in some space like RD, family objects in RD. So the intersection graph of F, so denoted G of F, is the graph with one vertex per object, XBO per object, O in F, and edge VO prime if and if O and O prime intersect. So O intersection O prime is not MC. So I will just give it's a very general definition. Maybe you know some intersection graph families like string graphs. They are super famous. But I will focus on some specific class of those intersection graphs, which are kind of close to what we call unit ball graphs. So let me give you some special cases. So first, if F is a family of unit disk in R2, unit disk in R2. So G of F is a unit graph. Graph. So maybe some of you are familiar with that. The idea is that we draw some unit disks, so all of them have diameter or radius 1, but equal radius, and we put one vertex per disk, and we add an edge whenever both intersect. So with that. Okay, so that's a good illustration of this kind of geometric graphs. And so I will be interested in also two generalization of those graphs. The first one, I will increase the dimension. So I would say I will consider a unit ball graph. So D-dimensional unit ball graph. It's exactly what you think. Instead of considering R2, we take RD, balls in RD. And a third one, because in practice, usually you don't have really disk. For example, if you take a Wi-Fi network, the range of the device is not a perfect disk. You can have some noise. And so usually we consider similarly sized fat objects. So a family, let me will write the definition here. So we say that a family of F is similarly sized beta fats if for every object O in F we have two balls B in and B out, two balls, such that we have the object which is in between up O and B out. We have the radius of B in, which is 1, and the radius of B out is beta. Okay. Do you have any question on that? So the idea is that you have something which is an object which is close to a ball. So for example, you can take something like that, a family of objects like that, and then you can take, you have, for this object here, you have an opposing ball, and it's the ball in and the ball out, and the radius between the ratio, between the radius needs to be a constant. Okay. So it's objects which generalize unit ball graphs. And in fact, all the results I will present, I will just state it for d-dimensional unit ball graph, but in practice it works for every similarly sized beta fat objects for beta constant. Okay. So keep just that in mind, that in general people are interested in proving some algorithmic results for this kind of geometric intersection graph. But in practice, like the techniques you use, you can only prove for unit ball graph, and usually it works well for this kind of graphs.
So these radii, I can see it's 1, the B in is 1?
Yeah. It's just that you need to, if you take just fat objects, you just want the ratio between the two balls to be at most beta. But if you want similarly sized beta fat, in fact, you need each object to have almost the same size, and so one way to do that is to fix the size of the ball in. Okay. So yeah.
Different objects may have different shapes.
Yeah, and they can be non-convex, non-connected, for example. For this talk, we don't care. So now we can give, in fact, some kind of informal definition of a robust algorithm, but which will be super important. So a graph algorithm is robust if it uses inputs, so it's informal. Only G of F and not F. So what does that mean? Is that I don't need the geometrical representation in input. For example, if your algorithm works on unit disk graph, you just want the graph, okay, and not the unit disk, the centers of every disk. Why? Because in practice, it's hard to compute this geometrical representation when you have the graph input. Yes?
When you say it's hard,
it's hard, yes, it's NP hard in particular, and it's complete for some existential theory of reals, for some class of graphs. And to push a little bit, it's ever, in practice, it might be interesting also. For example, in some cases, we don't know at all the geometric representation of objects, we just have the graph. Why? Because some antennas can detect one another, but we cannot really compute the geometric objects. So it's, even in practice, it might be super interesting to get some robust algorithm. Okay. And so now, in fact, I can already state my main results. and we will go into some other details. But so the one I will go into detail is that we will prove that there exists a robust algorithm for Hamiltonian path. We do a Hamiltonian cycle, but we have everything. I will just do on a d-dimensional unit ball graph. D-dim unit ball graph, so I will unit ball graph. Running in time. This time 2 sub O of n 1 plus 1 over 2. So in particular, when t equals 2, we have the square root phenomenon. Okay? We have 2 to the power of square root of n. And it's tight under the exponential time hypothesis. And what is nice about that is that there was a huge paper in 2018 where basically they proved that almost all classical problems they admit some subexponential algorithm like that. And for almost all problems, it was robust, except Hamiltonian path and Hamiltonian cycle. It was the last classical problem for which such an algorithm was not was yet to be found. Okay. But since more than 10 years, a non-robust algorithm was already known. So I will go a little bit into detail for this non-robust algorithm, because we will use some techniques introduced for this algorithm. So it will be, let's say, the A part of my introduction.
So for d equals 2 is tight under this hypothesis for larger values of d?
It's a tight for every d, every fixed d. Okay. It was proved in this huge paper of the Berg. But let's start with the non-robust algorithm from Ido and Ushida algorithm. So it was quite simple, but with a very nice idea and one very key lemma inside, which was very nice. So the idea is like, I will do just the sketch of the proof of theorem 1, non-robust version. So it's exactly the result of Ido and non-robust. So the first step is to compute the clique partition of the graph. Compute a clique partition. Let's call it P, Q1 up to Qt of E of G, such that, so we will need two properties, and I will just draw how we actually get this clique partition, and we will easily see what property we obtain. And just, I will do it in dimension 2. It's the same for the, if we increase the dimension. So the idea is to take, in fact, a very large grid, okay, but with very small cells. So in particular, we will want the diameter of each cell to be at most 1. And so what happens is that, okay, if you take this inside, it will be a clique. So we just put a grid, and then directly we obtain a clique partition. Okay? Because in this case, we have the geometric representation. It's the non-robust version. Okay? So we take this grid partition, and what we observe is that if we call GP the quotient graph of P, so it's very easy.
So a single block in the partition are all the drifts that have a center in the single cell?
Yes, sorry, yes, that's the clique partition we get. So the quotient graph GP, it's just that we take one vertex per click, so T vertices, and we make them adjacent if only if there is an edge between the two clicks. That's the definition of the quotient graph. And what we observe here is that, okay, if I have a unique disk here, it won't see too far away. It won't see any click here. But you can see, if we take one vertex here, it will see maybe some disk here, maybe some disk here, maybe some disk here. But what we can see is that the maximum degree is bounded in this graph. Okay. So GP has bounded maximum degree. We call it delta. Okay. And what we can see also is that the tree width of G of P is big O of square root of, let's call it T, so square root of n, where n is the number of vertices of my input graph. So what very simple way to see that is to say, okay, in practice, this graph might not be planar, but it's very close to be a planar graph. And in particular, if we increase a little bit the cells if I take cells like that, then the adjacency will be planar in some way. Okay, and so we can use the planar separator theorem to say that this graph has three widths square root of t. But then inside we have a constant number of clicks, and so we can just blow up the tree decomposition by replacing each large cell by the constant number of cells inside, and we obtain a tree decomposition of width square root of n for this graph. Okay. Do you have any question on this step? And in fact, it's the only step where we use the geometric representation. And it was like the huge problem was computing such a click partition. Okay. And we will bypass this computation in the next in the Rubus algorithm. But let me introduce the key lemma they proved. So the second step was to mark some vertices. I will state their lemma, which is very interesting. So the idea is that if G, I will say, there is, we can compute in polytime subsets, let's call it Eij in Qi times Qj and E of G. So we can compute a subset of edges between two adjacent clicks with the following properties, such that upsize constant. So in practice, it will be big O of delta square, so constant in our case, such that G has an Hamiltonian cycle, if only if it has one using only edges from Eij between clicks. I will just put it formally like that. So what I mean is that, okay, I can in fact, between each click, compute a constant number of edges, such that I'm sure that if I have an Hamiltonian cycle, I will go through these particular edges between the clicks. Okay. And what is super nice is that they prove that we can just compute them in polynomial time. And just to give some idea, it's just that in practice you always have an Hamiltonian path which goes through only two edges we need to find these two edges. And so how they do that, they say, okay, we can compute some matching between the two clicks. We add several edges, and we are sure that we can kind of reconfigure the path such that we use those edges. Okay, I don't go into detail.
So using all the edges from the ETH-tight means that that there might be some edges of the ETH-tight that are not used. Or it's exactly this.
So there are two kinds of edges that I will use. So the one inside the clicks.
Yep. Okay,
that's the one which are not in ETH-tight that I can use, but between clicks I use only edges from ETH-tight.
But you're not forced to use all edges from the ETH-tight.
No, just some of them.
And this delta is just a constant from the partition.
Yeah, exactly.
Okay.
Exactly. And so now that we have that, what we can do is say, okay, call them blue edges. We'll call them blue edges. Call them blue edges. And we'll call blue vertices the vertices adjacent to at least one blue edge. So if we come back to, let me maybe make another drawing. So the idea is that, okay, I have my clicks bi, g, I might have many edges, but I have some blue edges, and a very small amount of them, constant number of edges, which I'm sure that if I have an Hamiltonian path, then there is one using only two edges. And so, in particular, I will just mark these vertices. And so I'm sure that the Hamiltonian path will enter and exit this click by those blue vertices.
The B's are Q's?
Yes, sorry. And so what we will do then, we will constrict H by contracting all the non-blue vertices inside one click. So I replace, maybe I had many vertices here, it was a click, with maybe some edges. What I do now is that, okay, this is G, now I construct H. We keep the blue vertices, except, so we have the same, is blue, 2, 3, 4, 5, 1, 2, 3, 4, 5. But this one, we contract them into only one vertex. And we keep only blue edges. And actually, what they proved is that G is Hamiltonian if only if H is, and actually we can construct an Hamiltonian path of G just by constructing one of H. That's the important thing.
Given that, this is trivial, right? This is trivial if we know that these blue edges.
Yeah, exactly. Yeah, this part is just a consequence of the lemma. Yes. And then the important part is that, okay, in fact, H has 3 widths. So it is very easy. Same, the 3 widths of H is square root of. Why? Because the 3 widths of G of P was square root of n, but then here in H, I just have a constant number of vertices. I have a constant number of blue vertices because I had a constant number of blue edges adjacent to one click, and then all the other I contract them into one vertex. So the 3 widths of this graph.
The vertex is is a vertex adjacent to an edge EIJ?
This one?
Yeah.
We erase this edge. Yes. So maybe there was some edge here, but we can erase them so that we just keep these edges. It doesn't change the tree width. Like the trees doesn't grow.
Okay, so I also tried because I mean the cell is adjacent to, I don't know, 8 cells or something like this. Yeah. And you take a particular edge,
yeah.
IJ.
Yeah.
But then, and these blue are those edges in the EIJ.
Yeah.
But then, if I have an I cell and another neighbor, then some other vertices could be adjacent, incident to blue edges. And then you do it with respect to a single IJ or?
No, to all AIJ. That's,
so the white vertices are those that are not incident to any?
Yes, to any.
To any?
Yeah, to any.
Okay.
So yeah, you color every edge blue for every pair of adjacent.
Okay, then yeah.
Yeah, it stays constant.
That's true.
Yeah. And so the true width of edge is the square root of n, and then we can use classical dynamic programming to solve Hamiltonian path. And so we will use again this marking procedure in our algorithm. So keep that in mind, that we can mark this path. Okay. So just a small remark. So this algorithm was from 2010, something like that. But quite easily we can use the same method to, for example, solve in a subexponential time maximum independent set in this graph. How you can do it? You don't need the marking procedure. What you do is just you compute this click partition. Then you just take the tree decomposition GP, and you just take the tree decomposition of G induced by this one, like just you blow up each vertex by its click. And what you can observe is that it's a tree decomposition of 3 alpha of independence number at most square root of n. Then you can compute maximum independent sets in times n to the power of square root of n. But there is this annoying, so we obtain n to the power of square root of n complexity time for maximum independent set. But it's not tight because it's n square root of n again. And so we don't get from this technique exactly an ETH-tight algorithm for maximum independent set. And it was kind of one of the starting points of the work of the Berg. Basically, where they proved that there is a robust algorithm, ETH-tight, for maximum independent sets in this class of graphs. And I will go through this a little bit this framework because I will also use their tools in my own proof. So let's see the Berg framework. So maybe before going to that, do you have any question on this algorithm? Okay, great. So let's prove that was in 2018. There is a robust algorithm for MIS in the Berg graph running in time to 100. So I will just use the first step for my own proof, but I think it's super interesting, so I will go a little bit into more details. So the first thing we need to do is that, okay, we cannot compute the click partition. Why? Because we don't have we don't want the representation. We need it to be robust. So the idea was to say, okay, we will relax this condition on clicks. And so what they did is that, as the first step was to compute the click partition, is like to compute what they call a kappa partition. So P1 dt. So it means that each vi has a partition into kappa clicks. And such that we will obtain exactly the same thing as above, such that G of P has bounded maximum degree delta, and the true width of G of P is, I will note it in the dimension D this time. So the idea, just to like this proof of the bound on true width is not that easy, but the remaining is easy. I'll do it here. The idea is to say, okay, we can take a maximal independent set. Take a maximal independent set, any of them. Independent sets. So you just have some object. And then to obtain the partition, we take just the neighborhood of this maximal independent set. It will form a partition of the vertex set by maximality of this independent set. And actually, what you can prove is that since the objects are unit ball, this neighborhood can be composed only of a constant number of clicks, because you cannot pack too many balls inside a ball of bounded radius. And then the tricky part was to prove that the true width is a kind of square root of A. Okay. Just to give the running times, so this tree decomposition needs the tree decomposition is computed inside big O of in the subexponential type. I will just correct something, because there is one point which was very interesting in that proof, is that, okay, they say, in fact, we won't exactly consider the true width, but we will consider the weighted true width for some function, weight function. And so we call it weighted true width, and here I will just add for every gamma, any function gamma, such that I think the condition was it is a big O of t, not the same t, so x 1 minus 1 over d minus epsilon. So some small weight function gamma, then the weighted true width of this graph, where the weight of one vertex is gamma of the size of the click of the partition, sorry, the part, is square root of n. I will give an example of how we can apply that to solve maximum independent set. It's quite easy. We take
So can you repeat
this gamma
construction of the partition? So you start with a maximal independent set.
Yeah, it's like the construction is super easy. You take a maximal independent set, yes. And then you take just the balls around this each object, each vertex. And what you can prove is that it can be partitioned into a bounded number of clicks.
But the balls mean radius 1?
Yes, sorry, radius 1. Sorry, just the neighborhood. Yeah, sorry.
Oh, okay.
Yeah, because I'm working with kind of, yeah.
So, okay, so,
yeah.
and then if you just take a radius 1,
yeah.
Then obviously you cover everything.
Yeah.
Some vertices can be many.
Yeah, but we just choose arbitrarily. And just to be sure, in each VI, we know that there is a clique partition into kappa clicks, but we don't know how to compute it in a non-robust way. We just know that it exists, but we don't know how to compute it. Otherwise, it would be possible to apply the algorithm of Ito and Kushida, and we will solve.
Once you have your maximal independences,
Yeah.
when they roll, they are not cliques, right?
No, it's a graph which we know that there is a clique cover of size atmos kappa, but we don't know how to compute it. Okay. Yeah. And in fact, when they left open Hamiltonian path in the paper, they said, oh, the good way to solve the problem is to actually solve this problem, to compute the clique cover of each graph of diameter of atmos 2.
How does it help this maximal independences? Because you contract and it has bounded degrees, that's what you said?
Yeah, it has bounded degree, and it's not trivial. It's not trivial. Then you have to compute this, like to prove that the weighted reweights is this formula. It's one of the main results. So it's not trivial. I won't go into it.
What's the bounded degree? What is bounded degree?
Sorry, the graph of the quotient graph. This part. So this part is easy to see that there is bounded degree.
D, yes.
Yeah, this part is easy. This one is hard. Okay. And okay. I will just explain how we can use that to solve maximum independence, just because I think it's interesting. You take a gamma, the function which maps x to log x plus 1. And then what you do is that, okay, you take the tree decomposition of G, the tree decomposition of G. Let's call it induced by the one, it's not formal, sorry, induced by the one of GP. The idea is that, okay, we have the tree decomposition of GP, we replace each VI by its set of vertices, and we obtain easily a tree decomposition of G. And the idea is that, okay, we have the weighted tree widths of GP equals that. So in particular, for each bag, for each bag X, we have the sum of VI inside X, of gamma of VI, which is at most some constant times n over V. And so this is log plus 1. And so when we take the exponential, we have 2 super VI plus 1 is at most. So the product VI plus 1 is at most 2 super squares V. Okay. And basically, this VI can be partitioned into a constant number of cliques. And what it means is that in each bag, you have around that number of independent sets. Okay? And so you can apply dynamic programming. Like your dynamic programming table, in each node will have this type. And the key idea was to take gamma not equals to 1, because you have the classical tree widths, but to take something a bit larger. So now I have almost every tool to start to go into the proof for Hamiltonian path. So I will use these kappa partitions, and I will use this marking scheme. And now the idea will be, okay, I cannot compute the clique partition, but what I can do is that, okay, I can compute this VI which have small independence number, like a modern clique cover, and I will try to use this graph structure in order to maybe replace cliques with something which might be interesting for us. Okay, that's the idea. And this property, which will be interesting for us, is high connectivity. It will be the main idea. So we will replace clicks by something graph with high connectivity. Okay. And we'll prove that we can reconfigure everything. So, yeah. Okay. So, let's go into the proof now. And so the first thing I will need to introduce is the notion of Hamiltonian L-linked graphs. And it will be exactly the structure I want for each of my building blocks, of my decomposition. So it was, I don't know how to introduce this notion. So a graph G is Hamiltonian, G3 is Hamiltonian L-linked if for every set of pairs, set of L pairs, S1, T1, T2, SL, TL, there exists path P1 up to PL, such that two things for each PI goes from SI to CI, and second part, V of G, like the PI cover the whole graph. So V of PI. It's in particular, if the graph is Hamiltonian one linked, then it is Hamiltonian. Okay. Yes. Yeah. Yeah. Sorry. Okay. And what is amazing about that is that quite recently, so Fomin and its collaborators, was 2 years ago, I think, they proved the following. So if G is omega alpha of G L connected, then it is Hamiltonian L-linked.
So what's the connectivity there in the statement?
It's so you don't have any separator outside.
Vertex connectivity.
Yeah.
And then what's the function there?
Sorry, you see here, alpha is the independence number.
Alpha of G times L?
Yeah. If you are, like, they have a proof, like, I don't exhibit the constant, but if you are, I don't know, 100 alpha L connected, then you are Hamiltonian L linked. Okay. Yeah.
So the PIs must be disjoint?
Yes.
And the pairs also?
Yes.
So it's for all the pairs?
Yes. Any pairs.
But
Well,
different. Okay.
Yes. You can always find a cover. Yes. Exactly. And the proof is algorithmic. Like, so there is an algorithm which on input, S1, T1, SLTL returns the path, like verifying this condition, Q1 TL, or outputs that's alpha, in time, f of alpha of g L times a polynomial. So what they proved actually is that, in particular, Hamiltonian path is FPT in alpha. So it was their main motivation, was to study some problems parameterized by the independence number. And in fact, for us, it was super nice. So I won't go at all into the details of this proof. It's a wallpaper in itself.
Wait, FPT and alpha, but there's L here, so...
Yes. But in the case of a Hamiltonian path, you just care about two vertices. Okay.
But wait,
yeah.
But then but the condition you're checking is stronger. You're checking if you have a path between many two vertices, yeah?
Yes.
So maybe the graph is Hamiltonian, but so you're saying that this proves that Hamiltonicity is FPT in alpha.
Mm.
But you're checking this.
It is stronger, far stronger.
Condition, yeah.
Yeah. It's
So you might.
The graph may be not Hamiltonian.
Yes.
Like how does this? So the FPT algorithm
Yeah,
decide that the graph is not Hamiltonian. So
or maybe it will say, there is a large independent set. So it takes, more formally, it takes input KL. Either it returns the set of path or outputs that alpha is at least k. And the running time depends on is FKL times point.
Yeah, but then we just have the independent set. We don't have the answer whether the graph is Hamiltonian or not. So it's not really solving Hamiltonicity.
If you smaller than the number.
Yeah, I think that's something like that. You can ensure that you're not Hamiltonian if alpha is no. Yeah, that's
Either it gives you an independence that is larger than some alpha, or it gives you an independent path. So if your graph has if you know that the independence number is smaller than this alpha, then it will tell you.
Yeah, it decides the problem. Sorry, so it decides if it exists or not. And so in particular, if we apply it in the case where the graph is Hamiltonian and linked, yes, maybe it was not well stated. Sorry.
So my concern here, because Berg raised another concern, but my concern is that the graph might be Hamiltonian, but not Hamiltonian one linked. And I don't understand how.
Oh yeah. I see. So I try to simplify the result. The overall result is about some topological minors, and you can detect some topological minors in time FPT in the size of alpha in FPT time of alpha and the size of the graph. H we want to detect as a topological minor inside. And so it seems to be like, and if you take the you can decide if there is a topological minor embedding which covers the whole graph. Okay. Yes. And so this algorithm in FPT time in alpha and the size of H either puts a topological decide in times FPT in alpha if there is a topological minor embedding which covers the whole graph. It seems to be okay.
It should be rooted somehow because you have this ITI.
So this is a particular case of this topological embedding.
So this general topological embedding, there is some rooted thing that allows to have these terminals.
I think so. Or maybe it's just the tools. Maybe I need to go back into details in this paper. Yeah. But maybe we can just assume that in their paper they have one lemma, which in particular can say, okay, if I have small alpha, then I can take this part and compute that in polynomial time. Okay.
If I have small alpha, then what?
So sorry, maybe I can go into the rest of the proof, and if you at some point I will use this kind of lemma. So maybe.
Yes, but this is simplified. This easy thing you will need to use is that if you have bounded alpha, then what?
So we will ensure that our graph is our VI will be Hamiltonian L-linked for a very large constant L. Okay. And so we will ensure that there exists for every pair of vertices some path which cover this subset of vertices. And then, basically, in the paper, they have an algorithm to find this path. Okay?
This is good.
Okay. But maybe we can come back to that if you want after. So, but what is really important, in fact, is like this is the algorithm. Maybe we need to rephrase that, but this is so quite rapidly. The idea will be that we can compute in polynomial time. So, step 1, we can compute in poly time a partition of E equal such that GP has 1 degree, we just apply the same idea, and 3 widths, this time 3 widths, we go of n plus d, and each VI is either a clique or Hamiltonian lambda linked, and I just noticed that I didn't fix lambda. So there is such that for every lambda at most delta is delta where the delta is the maximum degree. Okay. Sorry, yes.
No, the second part you also asked that this VI is a small independence number.
Yes.
And that's where you're having.
Yes, exactly. And small and independence number, independent alpha at most. Okay. So in fact, delta and kappa are constants, and I can fix lambda as large as I want compared to delta and kappa. Okay.
So it's a good small alpha, right?
Yeah. So I will just do the proof of that. It's quite simple.
But sorry, one question. If a set is smaller than 2L, is it L-linked or is it not L-linked?
No, it is not. It has to be, it has to be at least of size at least and the definition is not monotone of Hamiltonian L-linkness. So in our case, we will have some kind of monoticity because we consider the connectivity. So we use the fact that if you're, the connectivity otherwise is monotone. So you can be, for example, I don't have any example in mind, but it might be possible that you are Hamiltonian 2 linked, but not Hamiltonian 1 linked. But in our case, since we will prove that we are connected enough, we'll have all the Hamiltonian L prime linked for every L prime. Okay. And so the proof of that is quite simple. So of this first step, of the fact that we can compute such a P. So we compute the kappa partition of the Berg. partition. Let's call it V1 prime. I gave partition of V, so that each VI has a click over of size atmos kappa. So we fix for each I in one prime. What you do is that, okay, the VI, what you do is that, so we consider VI, if it has the kappa L separator, then we remove it and we continue. We construct a separator tree. So here we have a separator of G of VI and I of size at most kappa lambda, and lambda I will fix the function G, fix G function, and we will like fix it later.
So the kappa partition means that each block is covered by kappa clicks.
Yes, kappa clicks. We know that kappa is a constant. We know it, but we don't know how to compute this click partition.
Now you are starting to build this partition?
Yes. So
what is this? So you draw a separation G of VI.
Yes. So what I will do is that, okay, this VI prime, sorry, VI prime.
So we already have some blocks, and we
yes.
construct next block.
And we destroy these blocks into smaller blocks such that each of them is either a click or is very connected. Okay. And how we do that? Okay, if it's already very connected, I'm okay. It will be Hamiltonian and linked. Otherwise, there is a separator. So I remove it, and I do it recursively.
By removing it, you mean that it will constitute a new block, or what?
I'm getting to that. So
okay.
So I'm removing. I continue in each connected component, so that at the end I obtain these blocks here, the leaves, which are each of them is induce a kappa G kappa connected graph.
Or it's small.
Or is very small. Okay. But if it's small, in fact, I will consider it as clicks. Okay. And here, the nice part is that here, since we have at most kappa leaves, because the independence number inside each block is kappa, this is loosely at most kappa nodes, vertices, yes, nodes because of the tree. There is at most kappa for kappa nodes in the separator trees. And so we have at most kappa G kappa, because each has size at most kappa G kappa times kappa to the power of kappa vertices of G of VI prime. Okay, if we take the vertices inside, appearing inside such a separator. And so what we can do, we can brute force the click partition inside. We know that inside there is a click partition, and since this part is small, I can brute force the click partition into kappa clicks. So brute force the kappa click over. And in fact, it's in constant time kappa to the power of G of kappa to the power of kappa. Okay. So that's the tricky part. And so we obtain at most kappa subset which are kappa G of kappa connected, and kappa clicks. Okay. And using this lemma, we can fix G of kappa large enough to ensure that my graph is each VI prime is lambda linked for every for lambda large constant large enough.
So the final.
So yeah, so the final blocks will be which one? Which will be okay. Each VI prime, I replace it by these blocks on the list together with a click cover of the separators I found in my separator tree.
So this one thing is a single block.
No, I have at most like this set of vertices. Now you see it just as a set of vertices. Okay.
And then you compute the IC.
I compute the clique partition inside, and then for these leaves, I know that it is a connected clique.
So I
Why
don't
do
understand.
you know that it is already a clique?
Here, it's not a clique.
No, the leaves.
The leaves, it's just connected. We know that it's kappa G of kappa connected.
But it may be small,
Yes,
but not a clique.
but not a clique. Yes, in this case, I
Then
think
you just partition into
Single
yes, to singletons. Yeah.
So I don't get, because it seems like it's a full recipe. So, and the way you started to write was like you will iterate because you started with some V1, VI.
Yeah. So yeah. So it's not like it's more like for each we do this decomposition at each VI prime.
So where the VI prime comes from?
Oh, sorry. It's like it was written here. It was even here. It's the kappa partition from the Berg. It's the
What?
from the Berg, the paper of the Berg.
Okay.
Yeah, sorry. I need all the tools I introduced before the introduction. That's why it was quite long. Okay. So I know that each VI has a partition into kappa cliques. Okay. So now I'm almost done. The remaining will be quite fast. Okay, trust me. So I know that everyone now I have like my new clique partition, which is not a clique partition at all, but each part is connected. So that first I want to apply now the marking scheme of Ido and Kushida. But their marking scheme is defined only for clique partition because they want to reconfigure each path for clique. So let's add all the edges when it's not a clique first, as just a tool for the proof. So we start from G, which has this partition G, VI, G. So each VI, G is either a clique or is a Hamiltonian lambda linked for lambda very large. And so maybe it's not a clique, so let's say it's something like that. Then we add some red edges. Here is my red. So I will put orange edges. So we construct G times, which will be the same, but where we replace each VI by a clique when it's not a clique. Okay, it's quite simple. So okay. Then we apply the marking scheme. We can apply it because it has a clique partition, and the partition has still the properties of Ido and Kushida. It has bounded degree. It's a clique partition of bounded degree. So their proof just works the same. So we apply the marking scheme. We identify some vertices. Then we contract. We do the same as we did in the proof before. So to obtain H. So this time we have something like that. Then what we can prove is that again H has 3 widths square root of n, like n 1 minus 1 over d. So we can construct an Hamiltonian path of this graph. And then we need to come back to prove that we can reconstruct an Hamiltonian path of G. Like we need to put the equivalence between them. And how we do that? It's quite simple. If we obtain an Hamiltonian path of H, we can reconstruct an Hamiltonian path of G. If it's a clique here inside, it's the same. We do the same as before. But if it was just Hamiltonian L-linked, we can exhibit the inputs and the outputs of this path inside these cliques, and it will be like the number of in and out will be bounded. This L will be bounded, and so we can use the algorithm of Fomin to reconfigure each path. Okay. So it's just that the step which was easy for Ido and Kushida because they just had to reconstruct the path inside the clique, which was easy. Here we have to use the heavy machinery of Fomin and Paul. Okay, and then we can okay, we have the main result. So just so just maybe a few words. Do you have any question on that before I move? Because we have some result that I will just state without going into details at all. Okay.
So
yeah.
Not a degree is necessary to get this thing at the end.
Yeah.
You get how you have so when the block is highly connected, large.
Yeah.
Then it still has bounded degree in your setup.
So when.
So what's the argument? Where does it come from?
The bounded degree. So in fact, when you in G here, since we replace by a constant number of clicks of sets inside, Vi prime becomes some constant number of Vi. We still have bounded degree. Why? Because you maybe the original graph, this one has bounded degree. Yes, I use again the Berg argument here, and so since I replace each block by a constant number of blocks, my constant graph also has bounded degree. Okay. Okay, so maybe I will just state the other result we got because most of the open questions, in fact, for this exact subexponential field, for the classical problems, now everything is solved. Like for every problem, we know classical problem, we know a robust algorithm which is ETH-tight. So I don't know. There are still many problems for which the best algorithm, the robust algorithm, is not known. I think, for example, for Steiner tree, no, it's known, but for some variant, maybe it's not known. For example. But there are many works to do from the subexponential FPT perspective. So let's just give you the algorithm we got. There is a randomized, that's the first problem. Subexponential FPT, FPT algorithm for long pass in d-dimensional tunable graph running in time 2 to the power of k 1 minus 1 over d log squared k. So k is the size of the path we are looking for. That's the natural parameter times the polynomial. And robust, sorry, it's important. Otherwise, it was wrong. And so we use the same idea, the same decomposition here, but we have to go through other techniques to get the FPT part. And
long path, what is this problem?
So we are looking for a path of length at least k.
K is fixed.
Yeah, and k is the parameter. Okay. And so, for example, what is open? So first, it's open whether we can remove the randomized and the log square dependency, and also our technique only works for a long path and not, for example, long cycle. If we want to decide if there is a cycle of length at least k, we don't know how to do it in a robust way. And so, for just dimension 2, there are a bit more results. Why? Because we can apply bidimensionality. We can say arguments of this, something like, either we have a large grid, in which case we have a long cycle or a long path, or the 3 bits is
it's not induced, of course, right? It's not induced.
No, it's not induced.
It's induced.
No, it's not induced. And yes, but if we want something for any fixed dimension, we cannot apply bidimensionality anymore. It doesn't work starting from dimension 3. So we have to do some other techniques. And so it's widely open. It's still in progress. So So most of the work, remaining work, it's for that kind of questions. Thank you.